Welcome, my friends! In this video, I'm going to show you the graphs of many common functions as well as how to translate them. This is going to be a semi-comprehensive video on translations of graphs with a lot of detail, so strap in. Let's first talk about the graphs of the 6 functions that every algebra student should know. For every graph we talk about, I'm going to point out what I like to call the key points, which are the important points you need to know are on the graph of the function, and will make graphing the translations much easier. First, we have everyone's favorite, the parabola, which is f of x is equal to x squared. The parabola looks like this, and has the key points 0, 0, 1, 1, and negative 1, 1. It also has the points 2, 4, and negative 2, 4, but usually just knowing negative 1, 1, and 1, 1 is enough. Next, we have the not-so-different function, which is the v function, or f of x is equal to the absolute value of x. This function also has the key points of 0, 0, 1, 1, and negative 1, 1, but has the distinctive v shape that the parabola lacks. Next, we have the square root of x, which has the key points 0, 0, and 1, 1. It also has the points 4, 2, and 9, 3, which are sometimes handy to know. Now we get into the slightly less used functions. First, we have x to the third power. This function has the key points 0, 0, 1, 1, and negative 1, negative 1, and rapidly increases as x increases and rapidly decreases as x decreases. Now we have a few strange functions. First, with 1 over x, which is kind of a disjointed function with a vertical asymptote at x is equal to 0. This function has the key points 1, 1, and negative 1, negative 1. Finally, we have 1 over x squared, which also has a vertical asymptote at x is equal to 0. But this function is always positive, due to the square, unlike 1 over x. This one has the key points 1, 1, and negative 1, 1. The functions I have introduced here are what are called the parent functions. They are the most basic form of the function. All 6 have the key point of 1, 1, and most of them have 0, 0. This table is a good reference for you to come back to when considering these 6 important parent functions. For the rest of this video, we will talk about how you can translate these functions, which is just a fancy way of saying modify these functions in some way. Most of the focus will be on the first 3 functions, as they are the most common, but the ideas explained in this video can be applied to other functions, including ones not shown in this table. There are 10 translations that we will talk about. I'm going to introduce all of the translations now using the absolute value in the parabola functions, but the idea of the translations works for any of the functions we have discussed. For variety, and because I'm lazy in pulling clips from videos that I've already made to create this one comprehensive video of translations, 2 of the 10 translations will be introduced with the square root function. After that, we will look at a bunch of examples putting the translations together. Okay, let's get started. The most basic and easiest to understand translation is a vertical shift. If a number is added to or subtracted from the parent function, the graph must be shifted up or down the appropriate number of units. F of x in general just represents the function of x, which in our case is either the absolute value of x or x squared, and k represents a constant number such as 2 or 4. Adding a constant outside of the function shifts the curve up, such as adding 1. Here we have the graph of the absolute value of x plus 1 over here, and over here we have x squared plus 1. The graphs are exactly the same as we had in the parent functions, except every point is shifted 1 point up. Instead of beginning at the origin of 0, 0, these graphs are shifted up by 1 unit, so that they now begin at 0, 1. Subtracting a constant outside of the function shifts the graph down, such as subtracting 1. The graphs are exactly the same as the parent function, but every point is shifted 1 point down. Instead of 0, 0 on each graph, we have 0, negative 1 for both the absolute value and the parabola functions. We can also shift horizontally to the left or right by replacing x with x plus a constant or x minus a constant inside the function. This is where some students get a bit tripped up, as the rule is the opposite of what many people would assume. Replacing x with x plus a constant, such as x plus 1, shifts the graph to the left. Notice the graphs are exactly the same as the parent functions, except now instead of starting at the origin of 0, 0, we begin 1 unit to the left at -1, 0. Replacing x with x minus a constant, such as x minus 1, shifts the graph to the right. Notice each graph is exactly the same as it was, except now instead of starting at the origin of 0, 0, we begin 1 unit to the right at 1, 0. So adding to x shifts to the left and subtracting to x shifts to the right. Why is it this way and not the other way around? Well, consider subtracting 1, either to the absolute value or the x squared function. This is a shift of the entire function 1 unit to the right, as we see here. Now ask yourself, what number would you need to plug in to either function to get an output of 0? Well, you would need to plug in +1 for x. Plugging in +1 either gives us the absolute value of 0, which is 0, or 0 squared, which is also 0. That means that 1, 0 is a point on the graph of either function. Subtracting 1 from x actually means we now have to plug in +1 to get back where we started on the parent function, meaning this is a shift to the right. The same sort of logic could be applied to a shift to the left. Another translation we could have is a reflection across the x-axis. Normally, both of these graphs open upward, but if we have a negative sign before the function, they will now open downward. Here's the reflected graphs of the absolute value and the parabola functions. Instead of having the key points of 1, 1 and -1, 1 on the graph, our y outputs have been made negative, so we have the key points of -1, -1 and 1, -1. We can also have a vertical stretch or compression, and that happens when we have a coefficient on our x term. For example, if we have a coefficient of 2, that means all of our y values should be multiplied by 2. We no longer have the key points -1, 1 and 1, 1 on our graph. Now we have -1, 2 and 1, 2, which stretches the graph vertically. If we have a coefficient of less than 1, then the translation is a vertical compression. If k is equal to 1/2, that means all of our y values should be multiplied by 1/2. We no longer have the key points of -1, 1 and 1, 1 on our graph. Now we have -1, 1/2 and 1, 1/2, which compresses the graph vertically. We can also have a reflection across the y-axis, which is indicated by a negative sign inside the function. Here's the parent function for y equals the square root of x. Normally, we have the key points of 1, 1, 4, 2, and 9, 3 on the graph. But the negative sign on the inside of our function changes the sign on all of our inputs, or x values. So now we will have the key points -1, 1, -4, 2, and -9, 3. Connecting the dots, we have a reflection across the y-axis, represented by y is equal to the square root of -x. The last type of translation we will discuss is the horizontal stretch or compression, and that happens when we have a coefficient on x inside of the function, or in this case, inside of the square root. Just like with the horizontal shift, everything is a little bit opposite of what you might think. If we have a k value that is greater than 1, then the translation is actually a horizontal compression, where each x value must be multiplied by 1 divided by whatever the value for k is. For example, here is the parent function for y is equal to the square root of x, with our normal key points. If we have a coefficient of 2 on x, that means all of our x values should be multiplied by not 2, but actually the reciprocal of 2, which is 1/2. We no longer have the key points 1, 1, 4, 2, and 9, 3 on our graph. Now we have 1/2, 1, 2, 2, and 4.5, 3. The x values are multiplied by 1/2, which compresses the graph horizontally. If we have a coefficient on x between 0 and 1, then the translation is a horizontal stretch. And again, the values for x should be multiplied by 1 over k. If k is equal to 1/2, that means all of our x values should be multiplied by not 1/2, but the reciprocal of 1/2, which is 2. We no longer have the key points 1, 1, and 4, 2 on our graph. Now we have 2, 1, and 8, 2, which stretches the graph horizontally. We would also have the point 18, 3 when we multiply the x-coordinate of 9, 3 by 2, but that one doesn't quite fit onto this graph. Let's summarize all of the translations we have discussed. A vertical shift up is represented by f of x plus k, which means we must add k to each of our y values in order to move up vertically. A vertical shift down is represented by f of x minus k, which means we must subtract k from each of our y values in order to move down vertically. A horizontal shift left is represented by f of x plus k, which means we must subtract k from each of our x values in order to move to the left horizontally. A horizontal shift right is represented by f of x minus k, which means we must add k to each of our x values in order to move to the right horizontally. A reflection over the x-axis is represented by negative f of x, which means we must change the sign on all of our y values. A vertical stretch is represented by k times f of x, where the absolute value of k is greater than 1, meaning all of our y values must be multiplied by k. The absolute value here is just saying consider the value for k without paying attention to the negative sign if there is one. A vertical compression is also represented by k times f of x, but in this case, the absolute value of k must be between 0 and 1. The effect of this on the points is the same as a vertical stretch. Multiply the y values by k. Next, we had the reflection across the y-axis, represented by f of negative x, which means we must change the sign on all of our x values. We also could have a horizontal stretch or compression, which is represented by f of kx, where k is inside the function. If the absolute value of x is greater than 1, you actually have a horizontal compression, and if the absolute value of k is between 0 and 1, you have a horizontal stretch, which is opposite of the rule that we had for vertical stretches and compressions. The effect on our coordinate points is also a little bit backwards. Instead of multiplying the x values by k, it turns out that you need to multiply the x values by 1 divided by k, or the reciprocal of k. Let's take a look at some examples putting these translations together. Consider y is equal to x minus 2 squared minus 3. This is the parabola function, which has been translated. The function has been shifted to the right 2 units, indicated by x minus 2, and shifted down by 3 units, indicated by the minus 3. Typically, the parabola function has the point 0, 0, but the translation tells us to move this point. First, let's move 2 units to the right. Then we can move 3 units down. After the translation, we will have the point 2, negative 3, which is sort of like our new origin, or our new 0, 0. If you want to, you can even draw dotted lines to help you see the new pretend origin, if that helps you. If we treat 2, negative 3 kind of like our new 0, 0, we know that the parabola function normally has a point at negative 1, 1, and 1, 1. So if we move 1 unit to the left and 1 unit up, we should have a point on our new function, and another point if we move 1 unit to the right and 1 unit up. The points I have drawn are negative 1, 1, and 1, 1 if we think of our dotted lines like our new pretend x and y axis. Then we can simply connect the dots in the pattern we know that the parabola function always has to complete our graph. How about y is equal to 2 times the absolute value of x plus 3? This translation includes a shift to the left 3 units, indicated by x plus 3, and a vertical stretch by a factor of 2, indicated by the 2 multiplying the function. The first thing I always like to deal with is the horizontal or vertical shift. In this case, we have a horizontal shift of 3 units to the left. So instead of 0, 0 on our graph, we have to move 3 units to the left to get to negative 3, 0. So our new pretend origin, and also one of the points on the graph, is negative 3, 0. Now we need to take care of the vertical stretch. Typically, we have the points negative 1, 1, and 1, 1 on the absolute value function. But the vertical stretch tells us to multiply our y values by 2. So we should have the points negative 1, 2, and 1, 2 on our graph. but these points apply to our new shifted pretend origin. So these are the 2 points that we need. 1 unit to the left or right from -3, 0, and then 2 units up. Connect the dots in the pattern of the absolute value function, and you will be finished. Okay, how about this one? We have y is equal to -3/4 times the absolute value of x plus 1 plus 3. The x plus 1 tells us to shift 1 unit to the left, and the plus 3 tells us to shift 3 units up. The 3/4 tells us we have a vertical compression by a factor of 3/4, and the negative sign tells us that we have a reflection across the x-axis. Note that due to the vertical shift, this will be a reflection across the pretend x-axis, not the real one, once we determine where that is. So starting at the origin of 0, 0, we can move 1 unit to the left and 3 units up. So our new pretend origin, and also one of the points on our curve, will be -1, 3. Typically, we have the points -1, 1 and 1, 1 on our graph, but the -3/4 out front tells us to multiply our y values by -3/4. That leaves us with the points -1, -3/4 and +1, -3/4. But again, draw these points with respect to our new pretend origin. So we can plot these 2 points with respect to our origin. Finally, we can connect the dots in the pattern of the absolute value function to finish the graph. Okay, let's try one more. We have y is equal to the square root of -2x plus 1. Now this one is a bit different than anything we've looked at before. We are going to want to factor the inside so that we have a coefficient of 1 on x. If we factor out -2, we have the square root of -2 times x minus 1/2. This is now in a form for which we can determine the translations. It looks like we have a horizontal compression indicated by the 2. We also have a horizontal shift to the right 1/2 units, indicated by the 1/2. And we also have a reflection across the y-axis, indicated by the negative sign inside the square root. Note that since we are shifting, the reflection will be across the pretend y-axis, not the real one. Instead of starting at the origin of 0, 0, we start 1/2 unit to the right, at 1/2, 0. This is our pretend origin. Typically, we would have the points 1, 1, 4, 2, and 9, 3 on the graph. Instead, we need to multiply these x values not by -2, but by the reciprocal of -2, which is -1/2. We get -0.5, 1, -2, 2, and -4.5, 3. These are the points that we should plot with respect to our pretend origin. Starting at 0.5, 0, we can move 0.5 units to the left, and then 1 unit up to reach a point on our new curve, which is equivalent to -0.5, 1. For the next point, we can move 2 units to the left, and then 2 units up. For the last point, we can move 4.5 units to the left, and then 3 units up. Finally, we can connect the dots in a smooth curve to draw the graph of y is equal to the square root of -2x plus 1. Alright my friends, that finishes our video relating to translations of functions.